Hello everyone, welcome back to Shexa's YouTube channel. Please like, comment, share and subscribe, and please don't forget to click the notification button or the notification bell so that you get notified whenever we get a new video uploaded to this channel. Today we're going to look at ALP assembly language programming, and the topics to be covered include assembler directives, macros and procedures. Right, assembler directives, these are the words or commands that are used within assembly code. These words, they are not instructions. They are used to tell the compiler what to do, but not what to run. So what's happening is they are more like traffic lights. No vehicles will run over traffic lights unless it's an accident. No driver will run over a policeman who is giving directions to the driver to say park your vehicle there or reduce the speed or whatever the instruction, the directive is. You get what I'm saying? So these commands, these are just commands embedded in assembly code and recognized and acted upon by the assembler, but they are not instructions. When I say they are not instructions, I mean they do not execute to say process this data or give me this information. They work for the compiler, they work for the assembler, not for me, the programmer. You get what I'm saying? So that's it. They work directly for the compiler or the assembler. So here's an example of the program that we have for one example ORG directive. So ORG is used here. ORG, this value, it means the next instruction that is following this directive is going to be stored in memory starting from 00000, right? And then meaning to say this value, this instruction which is saying variable 1, which is saying define byte called variable 1 var1 and initialize it to 19, is going to be moved to this array. So it goes there. Then we have another instruction, we increment by one byte, we increment by another byte, we get this to that. And then we have another ORGH. Anything following this directive is gonna be moved to this address. So this Martin is moved to what? To this address 0010, and then this, it's just M that is moved there, A is moved there, and so forth and so forth and so forth. And then we get another instruction which is saying ORG 0018H. That's the instruction. This var 5 dB, we get it to 18. So 0018 is the address. So we have assume, variable definition, constant. All these, assume is one of the examples of assembler directives, right? So with assume, let's start with assume and get the program example from assume. So assume is just used to tell the assembler that the name of the logical segment is telling the assembler that the name of the logical segment should be used for a specified segment. For example, here our data is the one that we are referring to as a data segment. So you can see here we say ds, so that's data segment, and then here we say code cs, so the code is now referring to cs register. Since we know that cs is what is code segment, then this term is not the one that is being used to represent the code segment, right? Let's just try to say, when I say a here and then say a here, we just want to check if it's going to execute. So it's good to experiment. Wow, it's executing. So what does that mean? What does that tell us? It tells us that we are just assuming that code segment is called code A. So whenever I say code A, it means I'm referring to code segment. You get what I'm saying? So you may actually put your name here, and whenever you are referring to this segment, you may call it as that. So this is just an example that I want you to follow. Let's just test if it runs, then that's perfect. Assume CS is Shexa, and then data maybe it's my wife here. Maybe I may put my wife's name there. So that's it on assume. So you've seen assume working here. So these directives, they are not case sensitive. I may put a capital letter S here. It will still work. Let's just check. If it fails to work, then that's it. But it's not case sensitive, you see. So let's get to another. No, I don't want to say anything. Let's get to variable definition. So like I said earlier, whenever you want to declare a variable, you say define byte, define 10 bytes, define dd, define double, and so forth. So db, define byte. So these are directives. So these bolded text values are the directives: db, dd, dq, dt, d, wait, all these. But here just read this text so that you know what it stands for. So these are the directives that we have, and this is an example: variable define byte, like that, variable to define byte, is, and so forth. So these are just examples on how one can actually write these directives to define variables, like that. And you also have another directive called equi. Equi is more like some people call it an operator, but it's a directive which is used to do what? To define constant variables. So we've talked about a number of assembler directives, right? Let's now talk about how macros. Let's now talk about macros. What is it that we call a macro? A macro is just a group of instructions that we bracket and give a name at the start of the program. Using macro avoids the overhead time involved in calling and retaining from procedures. Right, so let me give you the syntax of how one can define a macro. Right, so the first thing is you give a name to your macro. Let's say you want to add 2 numbers, so you may give the name add 2 numbers to your macro. So macro, in other words, it's more like a function, or it's more like a method when we look at high-level languages. When we look at high-level languages, so a macro is more like a method, right? So it's a group of instructions that, if executed, they give an output that is expected by the programmer or by anybody who is using that. So macro is now our directive that is used to do what? To define It's our keyword which tells us, or which tells the assembler to say this is the what, the macro. And then we put our parameters in there. There's parameter 1, parameter 2, and so forth. So let's see. And then the code goes there, more code, more code, more code, up until we get to the end. And at the end you say end m. End m is another directive that is used to tell the assembler to say this is the end of my macro. You get what I'm saying? So here is just an example of a macro program which is where we define a macro. Alright, so what happens with this code? With this code you are going to learn a number of concepts. We have functions in here. We have functions, and you need to listen very carefully, right? Because I have defined a functional macro, so you need to understand what is happening, or what the meaning of each instruction that is within the macro section or group of code. Right, so this is display. Display is what? Display is the name of the macro, right? And then macro is our directive or term or keyword. And then message is our what? Message is our parameter. So make sure you understand this. These square brackets, they are not applied here. I've just inserted them to show you that all parameters are put here like this. If you have more parameters, you can separate them by the comma. So these are our arguments or parameters. Then what do? We say push AX. This instruction called push, it takes this value to the stack and it puts it to the top of the stack. It takes the value that is within this register into the stack. So push the value in AX to the top of the stack, and we do not know what the value is in, or what value is in AX. Then we push the value in DX to the top of the stack. Now when we say move AH, since this macro is meant to display, you will see what it displays. It displays a message, right? So we say display macro message, and then this instruction, this one, moving 09H into AH is a function which is used to request display. By requesting a display, I mean we are requesting to print a valid string. That's what we are requesting. So 09 is used to request to display a valid string, or to print a valid string. Then when we say load effective address DX message, what we are now doing is DX is used to when we want to work with strings. So what we are doing here is we are getting the address where our message, or where the message to be printed is, and we are loading the address to DX. I think you remember this from our previous lecture, where we looked at how one can get the address of a variable. So we are getting the address of this message variable, right? So we now say this int 21 is now saying whatever that we have requested for, please do it. Get what I'm saying? So it's saying whatever that you have requested for, please do it. So what is it that we have requested for? We have requested for the display and to print a valid string. And when we say load dx message, it means we are now loading the address of the value to be printed. And what is it that we're going to print is the message, which is residing at an address that is inputted into dx. So it's more like we are saying, I want to display a string. So if you move 09 into AH, if you move 09 into AL, it doesn't mean anything. But if you move it to AH, it means you are requesting to display, or you are requesting the screen. And what do you want to do? You are printing a valid string. You get what I'm saying? So you will see what happens as we emulate. So int 21 is the one that gives permission to all requests. So it's more like an interrupt, or it's more like a function. Int 21, interrupt 21. Now when we say pop dx, we are now getting the value from the top of the stack to dx. Is the opposite of push. So we pop the value that is in the top to ax. You will see these instructions as we do stack programming in the next lecture, which I think will be done tomorrow if nothing disturbs us. Right, so we pop the value from the top of the stack to ax. So pop, it says pop to destination, push from source. Right, so we get to our data segment. We define the message now, message variable, and then it's a offsize byte, and then it's initialized to these values. So it's a string, right, with 10, 13 and so forth. This 10 and 13, this 10, 13 and the $sign here, you will see as we execute their functions. Then we define another second message variable of size byte with these values. We define another variable, and then we get into the code segment here where we say dot code. All right, and then we declare our label, which is called start, and our start ends here. Right, so we initialize ax with the values of the data segment, and then we initialize our data segment register with the value, with the values that we got from the data section of this code. Now we are calling our macro. You get what I'm saying? So we say display what? We are displaying message 1, and which is message 1? I am teaching macro usage. I'm teaching macro usage in x86 ALP. Then we go to the new line. Then we say display second message, meaning to say what is happening is, let me repeat the code here. So when you call here to say display message 1, what happens is message 1 is this one. So this value is then taken to there, and then it says display macro message 1. Then push ax. We push the value that is in ax2 to the stack. We push the value in dx to the stack, meaning to say we want to keep these values. So we temporarily put those values into the stack so that we will get them back, because we want to have the track of what we are doing. Then we say we request the display, and then we take the message 1 value address into dx, and then that's requesting to display, that's telling the assembler to say the message to be displayed is residing at an address that is moved to, or that is loaded into dx. Then we execute it. When we get to at the end of our macro, we then come back and call display 2. It displays the second message, and then we go to the that and displays that. So let's emulate it and see what I was talking about. So this is it. We start with the data segment. Alright, then we say single step. Then we are initializing AX with all the values that are in here in the code segment, in the data segment, or in the data section of our program. Then we initialize our data segment, and after initializing our data segment, what's going on now? Please don't get confused. The lines that are going to be executed are the ones that are highlighted in yellow. So this is the next instruction to be executed. Alright, so click next, and then when we say display message 1, it now goes back to, we are now calling this macro. Get what I'm saying? We are now calling this macro, but what happens is, look at it now. We say run and run. It doesn't go back to these instructions and run up until we get to the end, because we do not have that overhead of calling to say, I'm calling that, so I need to go to there and do that, like what we do in when we are using procedures. You will see when we run a procedure, the moment I say call, I call a procedure here. This yellow highlighting color, it will go to this line and start to execute. Once done, it then comes back. So let's check. It happens, it runs. All these instructions have been run. Now we've displayed I am teaching macro usage in ALP. Right, let's run. Next instruction, next. So you see, it has been executing this. It's still executing this, but it's not yet done. You will see it moving to the next instruction. Now it's done. So you see the message here. Then we next up until we are done. It has printed our last message, which is this one, which is saying I have played my role, please play yours. Shexa is going now by. You know what I'm saying? So let's now check. Did you see, are you seeing 10 there? No 10, no 13. Any dollar sign? No dollar sign. Why? Let's now check. Let's learn together the meaning of these values. Let's say we put 12 here, and to emulate, and instead of going step by step, let's just run it. You see the value, nothing changed, but we have changed the first value here to 12. Let's say we change from 12 again here. Let's say, let's put 32 there and run it. We run it, right? Nothing is changing. You get what I'm saying? You will see some changes. You will see some changes, right? Let me change. Let's put 10 back. Nothing changed, right? So we don't need to worry about all those values. So let's put 32 there, and then just run it. Now what happened? What happened? Where is our first line? Where is our first line? So this first value, it's just telling us the amount of space to be printed before you print this text. So so it does representing the amount of space to be that is indenting or indentation. That is indenting or indentation. So let's try to change it again to, here we have 13, let's have 3 here. Let's have 3 there and run it to check what happens. You see now 33, it gave us this kind of text. I hope you've done whatever you've done. You see, this is the first line, second line, third line. So These values, they are used to define the spacing before we start to print our lines. So it's, in other words, it's just telling us how the text is going to be printed. Let's now say, let's put back our normal values in there. Okay, let's put back our normal values there. Let's put 18 there, and then here we put our 10 and emulate. Right, so let's just minimize it and run it. Right, we've removed did we remove a dollar sign? Let me check. We didn't remove any dollar sign, so let's remove this dollar sign here. Let's remove this dollar sign here, and then emulate it and run it. We don't want to waste our time. Let's just run it. We see now how many lines do I have. I've repeated that line and that line. So dollar sign is now used to avoid this repetition. It's avoiding this confusion of repeating the lines. So it doesn't know that you are done running this this instruction. Then what happens is it will continue to run up until the next instruction's time is arrived. Once the time is arrived, they will execute. It will stop there, and then the next instruction is executed. So that's it for that. Thank you very much for being with me up to this stage. Let's get to another I don't want to save anything. Let's get to the next directives and concepts. We have EQ, talked about it. Print text on screen, right? So we want to print text on screen using what? EQ, we've talked about EQ. Let's just open this. Let's just open this and run it. Here, what are we saying? We are saying we've declared our variable with this value. Okay, fine. Now we have constant called, we have our constant called constant, which is initialized, which is assigned to 1, 2, 3, 4, and then we have Constantino, which is given 1, 2, 1, 2 as the value, and then we move AX and we move to BX. So this is the EQ, is just a directive that we are talking about. So let's just run it and check what goes to AX. Let's just check 1, 2, 3, 4, which is this one, and then next we were just showing that being EQ or being E, big Q and U doesn't matter. It's not case sensitive. That's what we wanted to illustrate there, right? Printing string on the screen. I think we've talked about this in our previous slide. But now, previously we printed a string on the screen using the values 10, 13 and $sign. But this time we don't want to use those numbers, and here is what you are supposed to do. Like I said earlier, to say this lecture has got many concepts that are being covered, so make sure you listen attentively. Listen attentively. Right. So here, what are we doing? Inside the data segment or data section of our code, we define our bytes, and in this case we have our first string, first text or string printed by Shexa, and then we have second string that will appear because we are having a carriage return. So you'll see what we mean by this. So the first thing is, in this case now, it's a procedure. So this is the main procedure. It's a procedure called main. Right? So main procedure ends here. Right. So what is happening is we are now initializing our DX with DS register, and then what happens next? we put the address of our string. Remember that whenever you want to print a string, the address of the string must be residing in DX register. And then AX, you put 09 or just 9 to ask for display, and then to request for display or to request to display a string. So whenever you say move AH9, it means you are asking to print, and what you want to print is residing at an address that is loaded in DX. And then int21 means please execute or grant. We are now granting permission to all the requests that we have received. So what request of printing the string that is residing in there onto the screen. Right. So moving to as well is another function, which is what a carriage return to say, let us go to the new line. So if you move, the moment you move 2 into AH, if you are dealing with the screen and printing strings, you are telling the assembler to say, now we are going to the next line. So we then move D into DL, then int21 to grant all the requests that have been put in place by these two instructions. This one and that one, it's a combination which result into carriage return. Then we move to DL A. So the next line value is residing at an address called D, and this D then put into DL. Then same applies, remove this one. So line feed, it avoids deleting existing lines printed earlier or preserves existing printed lines. You will see when we start to experiment with this code. Then int21 is now executing this. So int21 is just an interrupt which grant permission to the request to recently requested processes. And then here we now load and display string number 2 like we did here. It only differs that we are now printing string number 2, which is this one. And then we are done. So if you want to retain control to DOS or to operating system, what you do is you move into AH4C, then you execute this request of retaining control to DOS operating system. Right, so let's emulate our program and observe what happens. Right, so this is our code. Right, we go single line, we initialize our data segment, then we get the address of our variable with string number 1. We then request for display, then we grant permission. So by the time we finish executing int21, we get this string, which is first text or string printed by Shexa. First text or string printed by Shexa. Then we go to the next. We are now telling our assembler to say, let's go to the next line. Then going to the next line is achieved. Then what do we want to do? Avoid deleting these lines that we have printed already, and avoid also repeating those lines. Then we execute, and then we go to the set of three instructions to be executed so that we print the second string. The moment we finish running this int21, we do it that way. Second string will appear here because we are having a carriage return. So we are done. Let's run. So it's more like we run it like that. So that's it. We are done with this So let's try to experiment. Let's start some experiments. We've said if we, let's just say, let's comment out this one and try to execute. So what we have commented is the request to have the display and the request to display the string. So let's try to emulate it and see what happens. Are we going to have the first string printed? We just have our screen was int 21 grants permission to say it's an interrupt. So an interrupt is executed by or is defined by disturbing the normal flow of the program. So it will give you the black screen and request for input. You get what I'm saying? So in 21, without anything, it will just pop up the screen. Nothing comes up. So we may say enter, we put say enter, and then run. The next instruction, run. But other instructions, they will run normally. You will see it comes, but we do not have the what? The first line. So that's the experiment, first experiment. And then the second experiment. Okay, what if I request and don't get permission? I don't get permission since int21 grants permission. Right, let's run. Nothing is printed. We don't have we have requested, but we didn't get permission, so nothing is going to be printed. Let's just run and see if we are going to have the second instruction printed. So when we do this, we put our carriage return. We cannot put a carriage return without the screen, so that's why you saw the screen coming up. And it's also because we have int21. Then we run, our second line appears. So we now know int21 works in the int21's functions. Now if we remove all this, let's just remove this, all this set of instructions, and then try to run it like that. We run it, let's just run, let's go step by step and see what happens. First text was string printed by Shexa. Perfect. Then we go to that instruction. It avoids the deletion or repetition of this previously printed line. Now it prints what? First text string printed by Shexa. String printed by Shexa. Right. So this one we have removed. Sorry, this is our carriage return which we have removed. But now look at what is happening. It's now printing it's repeating the text that we have already printed because we didn't go to the next line. Then single step, you see what happens. So we need our carriage return to avoid all this. So carriage return allows us to get to new line, and also helps in avoiding line or text repetition. Let's now comment on this one and see what happens. All right, let's just execute it. First string is up. Oh, it's all printed in one line. So it didn't feed to say we want more space to print. So our first line was printed here, right? Because we didn't feed to say let this line be the second line now. It just overrides what was printed here with the second text. So that's the purpose of this one, to avoid overriding or writing on top of the other of the text that was printed earlier. Then this one is the same as this one in terms of printing the text or displaying the text. So this is the code to display text message or to display a string. Right, so that's it on this concept. Let's get back to other concepts now. Procedures, core and retain. So let's just get back a bit and say, right. It's fine. Let's just go to the one that we want to run. So call and retain instructions in a procedure. So what's the syntax for this for procedure definition? You say procedure name, then you say proc, we're done. Then procedure code goes here, and then you put some instructions, more instructions, and then you say retain. So when you want to call this procedure, that's when you use the term call. But when you want to end the procedure, that's when you say retain, which is RET. Let's look at alright, and then we end our procedure like that. Procedure name, and then we say end P. Let's now look at an example of a procedure. Right, so what is happening here is this procedure. What happens with it? We have declared our procedure here called Shexa, right? So all these are the instructions to be executed, and all this is calling the what? The procedure. We are calling the procedure. We call the procedure, we move. We call the procedure, we move. We call the procedure, we move. You get what I'm saying? Right. So what happens is we move BH to 0, then we call the procedure. By saying call, it gets here, and then we move 2 into CH. Then 2 is added to the value that is already existing in BH. You get what I'm saying? Then when you say 30 plus the value that was already in BH, we get a certain value. So if you want to print a value, or I mean a character or a number, if you want to print a number onto the screen, you need to put 30 into, if you want to print a number, for example 30 or 31, 32, 33 up to 39. Sorry, I made a mistake. If you want to print a 0, 1, 2, 3, 4 up to 9, you put 30 or 31 or 32 or 33 or 34 or 35 or 36 or 37 or 38 or 39 into DL. You get what I'm saying? So here we want to print 1, we want to print 2. So the main process, the main purpose of this program is to print 2, 4, 6, 8, the multiples of 2. So what we're going to do is we will move 30 and then we add 2. So we start with the 2, 32. To print a character 0, you need 30 value. This only works for values from 0 to 9. So that's it. We move BH, we move 30 into, we add 30 to 2. We have 32 now. When we say move AH, comma 2, we are now inputting 2 in AH. You get what I'm saying? So putting 2 into AH means something. So putting 2 into AH is a function which is used to print a character. And the character to be printed will be residing in what? In DL. That's why I was saying 32 must be in DL, and 32 is what? Is 2. If you want a 0, you have 30 in DL. You are not getting what I'm saying. Alright, let me start again. What I'm saying is, whenever you put 30 in DL, and you all right, let me start this way. We move to, we want to print 2, 4, 6, 8, 10 and so forth, and there you go. So what happens is we say 2, we move 2 into ch, then we say this 2 plus bh, the value in bh, of which the value in bh was 0, and then 30 plus the value that was moved or that was added to bh, which is what, 2. It becomes 32. So when we have 32, it means we can print 2, right? Then next we write a function instruction which requests for printing a character, right, which is 2. So whenever you put 2 into AH, it means we want to print a character onto the screen. And where is the character? The character resides in DL, and the character that is in DL is what? Is 32, and 32 represents 2. You get what I'm saying, right? So BH is what? Is 32, since we said 32 plus 30, 32. And then we grant permission to printing a character which is residing in DL. So DX is meant for characters and strings and printing all those. AH is meant for all the functions, all those functions that are requesting the screen and printing something onto the screen. And then we say int 21, which is granting permission, and then we end our procedure, or we can say return, which means we are now returning what? We are now retaining control to the DOS operating system, right? And then Shexa NP, we are now closing our procedure, and then we return as well that. So you cannot have 2 RET. If you have RET there, then this this procedure will not end. So let's execute it. So here we just say we are going to print 2, but after printing 2, control goes back, since we didn't say return. So we end, then we go back, we say 2 is now added to BH. So 2 in BH, we say 2, we call again here, and then we come here, and then we add 2 into CH, and then this 2 is being added to BH. BH has got what? Has got 2. So 2 plus 2, we get a 4, and then 30 plus 4, we get a 34, meaning to say we are going to move 34 into DL, which is the value to be, which is the character to be printed, and 34 represents 4, and here we request to print the character. And then we end, we get back again, we add a 4 into BH, 4 into BH, then 2 into CH, 2 in CH plus 4 in BH, we get a what? We get a 6. Then 30 plus 6, 36. We request to print 36, and by putting 36, we print 6. So 2, 4, 6, and so forth and so forth and so forth and so forth and so forth, up until we get to the end. So let's run it and see how it emulates. Single step, we move. Now we are calling Shexa. Look at what happens here, right? Single step, it now goes there, but with macros it doesn't do that. It just executes without calling. Get what I'm saying? Then we run all these instructions. We now have 32 there, meaning to say this 32 in BH is the one to be printed, but it must be in DL, it's there. And then we grant permission by running that. Then 2 is printed there. 2 is printed. Then we run again. When we get to return now, look at this. When we get to return, it then goes to this instruction, which is move BH2. Look at it. How does it know all this? Why didn't it go to the first one? You will know this in the next few seconds. It's because it's pushing some values to the stack, which is keeping track to say the address of the next instruction was this, and it's taken to the top of the stack. Then the moment we say return, it then pops the address of that instruction to say this is where I ended. Let me proceed from here. So it goes that it calls and then goes back to 4. It's now print 4, 6, 8. It's done because 6 is already printed, 8 is already printed. That's where we are ending. Right. So I assume that you now understand this. Let's get to the next thing. Let's not save anything. Let's go to the next thing. Right. So here now I want to explain the call and the return instructions or words or commands. Call, what happens with call is this. With call, let me repeat it here. When we say call, right, let me do it as we run here. Right, the address of this instruction to be executed, right, is the one that is available here in IP. Okay, then I say run. I've executed this line. Now the address of the next instruction to be executed is 0102, right? But it's now calling this one. You get what I'm saying? So the moment I execute call, I need to keep track of the next instruction that was to be executed, which is this one. You get what I'm saying? So the address of this instruction is stored into the stack, that is on top of the stack, right? Excuse me. So let me open the stack here so you can see exactly what we are saying. Right, so we have our stack here, and this is the top of the stack, right? But this one goes downwards, but don't get yourself confused. This small r is the one that is pointing to the top most or top word in the stack, right? So the address of this instruction is the one that is going to be pushed into the stack here. So if I say run, the address of this instruction is 0105. So that's the address of move bh2. So core instruction has pushed the address of the next instruction to be executed, because when we are done with the called procedure, you know what I'm saying? When we are done with the called procedure, we need to return and proceed or resume from where we have left from. You know what I'm saying? So we run this. So after we execute call, we push the address of the next instruction to be executed in the main line, which is this one. The address, this 0105 is the address of what? Is the address of this line number 8, right? So once that is done, the address of this move ch2 is moved into IP, which is instruction pointer. It's now pointing to the next instruction to be executed. So move ch2 is the one that is to be executed. You know what I'm saying? We go that way. Then all these addresses are the addresses of these instructions. We execute, we run all those. Then our 2 is executed because we have gone through all these instructions. Then we run. Then the moment we say return is now taking 0105 back into the instruction pointer, so that it knows to say I'm done with the called procedure. Let me go back and resume at the point where I have left from. And then the moment we go single step, you will see that 0105 is the one that was moved into instruction point, and now the top of the stack is now having 0 0 0 0. I hope you are getting what I'm saying. Then we go, we run again, we run. The moment we call, the address of this instruction is 010A, and it's moved into the top of onto the top of the stack. And then after that we execute that, and then the address of this instruction is the one which is this one. You will see that as we continue to run, 0111 is the one that is going to be inputted into IP, because we are going to call this Shexa procedure several times. Let's run it, run it, run it, run it, run it up until we are done. Our 4 is here because of all these instructions, right? So we move H, we move 4 into BH. You will see the after calling Shexa, the address of IP, which was 0111, you will see it again. You run. This is the address of this instruction. You run. 6 is there. You get back, 8 is there. So that's how it goes. So call, this is what happens with call. The moment you run call instruction, it pushes the address of the next instruction to be executed in the main in the calling procedure, right? Or in the calling code. The address of the next instruction to be executed in the calling code is pushed onto the top of the stack, and the address of the next instruction in the called procedure is moved into instruction point. That's what happens with the call instruction. Then the return instruction, what it does is it gets back the value from the top of the stack into the instruction pointer. Then normal execution proceeds. All right, so let's see some illustrations. Let's assume that we have our main line, or the calling program is running like that. It has got all these instructions, and the call instruction is here. The call instruction is here. All right, what happens when you get to call instruction? I have already told you this. And the next instruction to be executed in the main program, so the main program goes there, but it's interrupted here by the call instruction. So what happens? It's running from top to there. Then IP, the instruction pointer, gets what? The value that goes to the instruction pointer is 0200. Why? Because the next instruction in the called procedure is residing at 0200. But what goes to the stack? What goes to the stack is the address of the next instruction to be executed in the main line or calling program after call instruction. And then it runs the called procedure. So the called procedure has got its instructions here. Then it gets to return. Once return is executed, what happens? 0105, which was pushed onto the top of the stack, is then taken into IP to say the next instruction to be executed is residing at 0105, and the next instruction is this one, that is just after the call instruction, to say after we've run this called procedure, we then go back and start from this address. So you can see it going back, going to IP. So IP is now having that as the next instruction to be executed, and then it executes this and other instructions to be following it to be executed. So this is what happens. It runs, then IP is given the next instruction to be executed, which is in the called procedure, and then we execute it. When we execute run, return, IP, the value is then popped from the stack to IP. Right, so that's it. Let's see if we are having the main line program, and with the main line program, let's say we are calling a procedure which is also calling another procedure. Let's see what happens. Our main line goes to call, and the call instruction 0105, which is this one, is moved or is pushed onto the top of the stack. After it goes to the top of the stack, what happens? The address of the next instruction to be executed in the called procedure is moved into IP, like that. Right, so this is the next instruction to be executed in the called procedure. Then we have our IP having this value. Then this value is stored into the stack. Then what happens? This procedure also calls another procedure. Then when we execute the call instruction here, it moves the address of the next instruction to be executed in this procedure onto the stack, and then IP value then takes the address of the next instruction to be executed into the second procedure that is called by the second procedure. See that run call, IP is populated with the 0500, which is the address of this another instruction that was to be executed. So 0205 is the address of the next instruction to be executed. So this is what happens. 0205 is the address of this after running call instruction. Then the moment we have our call instruction here, the moment we say call, the IP register is populated with the address of the next instruction to be executed in the called procedure. It's called by this instruction, right? Then it calls there. The moment you say call, then the address of that one is moved to the top of the stack. The moment we say return now, that's when the value is then, the value that was put on top of the stack goes into that, so that we proceed with the execution of this second procedure. Then once we are done, this value that is on top of the stack is moved back into IP, so that we proceed to execute this instruction there. You see, it goes back, and then we have our IP 0105, and then we finish. So this is what happens. We execute, we call, then IP changes and the stack changes like that. Then we call again, our IP changes to that, and the top of the stack is changed to get the instruction, the next instruction to be executed in that procedure. And then when we call return, we get IP changed to 0205, and then the top of the stack is now the previous one. And then when we call return of this procedure now, this one, we get our IP populated with 0105, which is the instruction of this, which is the address of this instruction, and then we execute it. Our stack is now left with nothing. Right, the call and the return instructions. So this is what happens. Main procedure, the call procedure, first instruction goes that. Then the moment we call, here we call, we go to the first instruction into the called procedure. Once we are done, we go back to the main procedure and then execute the first instruction after the call instruction. Let me start again. We have our main procedure, which is this one, and it has got call instruction. The moment you call, it goes to the first instruction of the called procedure, which is this one, and runs all other instructions. And then when we get to return, it goes back to the first instruction after the call instruction. And if we have many or several call instructions, we keep a record into the stack and the IP register to know where to resume from. Right, so this is what happens. Here we have our main program, and here we have our stack. So I'm trying to explain this in different ways. So before we call, this is what happens. Our stack is pointing to nothing, or 0000, right? Then the moment we say call, this is the value that is moved into IP, so that we know the next instruction to be executed, right? It's not moved right there, but it's known to say after this call I must run this first instruction. So our procedure first instruction is lying at address 0200. So the moment we execute call instruction, this value is pushed into the stack, and this 0200 is moved into IP. You see, like this, 0012 is moved into the top of the stack, and the stack pointer is pointing to this value. Now 0200 is now moved to IP. Then that's it. That's how it goes. That's how it goes, before the call, after the call. So when we return now, we have executed all the instructions, and then the next instruction we execute is what? Is return. The moment we execute return, we now pop this value, and it goes back to IP, and then IP points to 0012, and then stack is left with nothing, and then we execute this instruction because we want to resume at this address. So this is what happens. Then stack is left with nothing, IP is now pointing at 0012. It resumes execution. Right, so that's it. Types of call, we have near call and far call. And with the near call, it is a call within the same segment, and it produces the starting address of the procedure by adding a 16-bit signed displacement to the contents of the instruction pointer. So we have inter-segment far call, that is called the far call. So it's used when the called procedure is in different segments. So that's it. Difference between near call and far call. Right, near call it's within the same segment, and far call is within different code segments. Then we have replace old. With near call you replace old IP with new IP, but with far call you replace old pair of code segment and IP with a new pair. Then with the near call, the value of IP is pushed onto the stack, and with far call, value of pair CS IP is pushed onto the stack. Also called intra-segment, but near call is also called intra-segment call, but far call is also called inter-segment call. So that's it. Take this away. Write an assembly language program that calls near and far procedures. Write assembly link and run a program which consists of more than one assembly module. And then you may also need to use a procedure to convert that code into what? Assembly language. What is the difference between that? What is the difference between end and NP directives? Given ALP program example which uses equal directive. Implement a standard assembly language program for addition of two 8-bit numbers. Describe how one can define the data structure in ALP. Right, thank you very much for watching my video, for watching me right now. May God bless you in Jesus' name. Goodbye.